Thank you. Could you hear me?
Yes.
Okay, so I will start. So my name is Fengping. I'm from International Center for Deep Life Investigation, Shanghai Jiao Tong University. And today my talk is about the microbial alkene metabolism, origin and evolution. And it's one of the most ancient life traits. And this work has been mostly conducted by Dr. FengpingWang from the same university, and also colleagues from University of Bremen, Günter Wagner, and Tom Williams from University of Bristol. So I will talk about alkane. We know that it is composed of hydrogen and carbon atoms. And today, I will focus on methane and the multi-carbon short-chain alkanes. We know that methane is the simplest organic carbon. And also there are ethane, propane, butane, pentane. And those short-chain multi-carbon are widespread in nature, and they are important energy sources. And in my group, we study a lot of those alkane-rich environments, including like continental shelf cold seeps, and also sometimes at hot springs, and there are also methane bubbles coming out. And we know that methane could be produced biotically and abiotically. And to produce methane, we know a process, methanogenesis. And to use methane, that is called methane oxidation, and the organism is called methanotroph. And there are common things between
Fengping, we don't see you moving forward in your slide. You're still on your first slide.
Really?
Yeah.
Can you?
We didn't see you moving forward. Can you try again?
Okay, but I'm moving it.
I think you may have selected a different window for your presentation. Maybe if you unshare your screen and then you share again.
Okay.
Make sure you select the window that has the presentation.
Could you?
Yeah, now we are on a different slide. If you can go, can you quickly go backward to the slides 2, 3, 4 until you're where you are?
I cannot move it now. It's strange. Sorry. You know what's wrong here?
Don't worry, we will figure it out.
Could you say this one?
Now, yes, we see this. And yeah, that looks good. Yeah, now you can switch. Do you want to go to presentation mode? If you want, you can also leave it in this mode. Yeah, no, this works. This works well. Thank you.
Sorry. Okay, so let's say, yeah, alkane and methane and short chain alkanes, which I most will talk today. And methane could be produced biotically and abiotically. That's methanogen and methanotroph. Methanogen that could produce methane, and methanotroph is using methane as an energy source. And there are pathways for methane production. And here shows, could you see here from CO2, and then these 7 classical pathways to produce methane. And methane could be produced from different substrates, which including CO2, acetate, and methylated compounds. And but they share here shows that they share the same 7 classical steps.
Fengping, are you still on the slide with the alkane list?
No.
No, okay. I think it's best if you don't use the presentation mode. You just go back to the mode when you're going out of your presentation, the one you just had before.
Oh, I'm so sorry.
Don't worry. If you share again, but now you don't share the presentation mode. Just share the normal mode where you can modify slides.
Could you see this one?
Yes, I would say just stay in this mode. I know you can switch slides here.
Okay, so you now can see the methanogens.
Yes, we did not yet. Yes, we did not yet see slide 3. Maybe you can quickly explain to us what slide 3 is about. Thank you.
Yeah, it's a simple one. So yeah, methanogens that can produce methane through the process called methanogenesis. And the methanotrophs use methane as an energy source. And so that is called methane oxidation. And here are the 7 steps from CO2 to produce methane. And methane could be produced through different substrates, like from CO2 and from acetate and methyl compounds. And all of these methanogenesis from archaea. And for a long time, we know that only Euryarchaea could do methanogenesis. And we can see these slides that methanogens and methane oxidizing archaea, in short, AMI, share many common features. Let's say in the middle, in the upper part is methane, and then here is the 7 steps and catalyzed by different enzymes. And the most important enzyme is this MCR, methyl-CoA reductase, that could used in the first step to oxidize methane, or in the next step to produce methane. And be aware of this core enzyme. I will talk a lot about it in my later phylogenetic analysis. And also in the second step is the MTR. MTR actually could link MCR with the other WL pathway. So this is the core pathway. And also that for methanogens, it's widely distributed, and methanogens has been isolated 100 years before, and there are a few model organisms to study methanogens. But for any, until present, there's no culture, pure culture. There's still there are enrichments. So we can divide the pathways for methane production into three modes. The first mode from CO2 to methane. In these pathways, the most important part I just highlight in red. The first is the MCR I talked about, and the MTR I also talked about, which linked the methane production with the wood-lindole pathway, that is the WL pathway. And the second part is from the methyl compound to CO2 and methane. And here it's also the MCR and MTR, but the wood-lindole pathway was run in reverse directions. And the third part mode is from methyl compound to methane. And here is a very simple mode. It's only MCR is involved, and there's no MTR, no WL pathway. It's very simple. So the question later on, what we want to ask is that which one is first and how the methanogenesis evolved. And besides the canonical urea acuta, we know they are methanogens, and in recent years, there are more and more new MCR-containing archaeas groups were isolated or found. Like here, the left Basia acuta was found in 2015 that it contains a novel type of MCR. And at that time, it was suggested that probably this Basia acuta could produce or oxidize methane. But then actually, the next year, 2016, Günther Wagner's group enriched an archaea and bacteria assemblage and shows that this assemblage could oxidize butane. And this is the first time show that archaea could oxidize butane. And this archaea contains an MCR, which is closely related with this Basia acuta. So now people largely believe that the MCR, the novel type of MCR genes from Basia acuta can oxidize multi-carbon alkanes such as butane, propane, etc. So we know that on the known history of our Earth, most of the part is resided only by microbes, and microbes not only negatively fit our environment, but on the other side, it can positively terraforming our environment. And so we know that there are a lot of different events, geological events, that is linked with microbial activity. So such as, which I would talk about, the FengpingWang paradox, and the glacial and deglacial events, and of course, the rise of oxygen. So what roles of methanogens have played? And as we know that methane is a potent greenhouse gas, so is it could be served as a very good model to study the interaction of microbial activity and evolution with the environment. So with these questions, we started methanogens and the methanotrophs in detail. So the question is, when anaerobic alkane metabolism originated and evolved? As I said before, methanogens has been isolated more than 100 years before. And after that, many different methanogens has been isolated, but most of them belong to urea acuta. We see the slides here, urea acuta. And then until 2000, and the first Emmy discovered, but it also belonged to urea acuta. And then later, different Emmy tags were enriched, and the Me2A metabolism was first clarified in my group. And then later, they are characterized what I said before about Basia acuta and butane oxidizing archaea was determined. And one thing I would highlight that with the boosting of genomic sequencing, and there are more and more new MCR lineages was found. And especially in 2019, that 2 years ago, from several different groups, including my group, find many different archaea groups could did have MCR genes and potentially have the function in alkane metabolism. And here we can see the archaea could be divided into TAC, ASCAT, urea cuta and DPANN for superfina, and except DPANN, all the other three superfina have the MCR. So it raises the question or a hypothesis that alkane metabolizing could be very ancient trait, and or maybe one of the most ancient trait in archaea. So we did phylogenetic analysis to check the evolution of this archaea. And this slide shows that the MCR phylogenetic tree coincides very well with the species tree. That means that this archaea with this MCR are vertically transferred. And then we can have a better look at the bootstrap value. That means the bootstrap value is very high, means that they are very much safe to say that they have this very strong relationship and could be divided into different clades. And here it could be divided into at least 4 clades: TAC, class 1 MCRA, class 2, and class 3, different clades. And we can see in this slides more clear that these methynogens could be divided into 4 clades, and this is the from the MCR gene, and this MCR gene tree coincides with the phylogenomic tree very well. That also means that those genes and those archaea inherited vertically. And then how about the MTR genes? Here we can also show that the MTR gene, they only existed in class 1 and 2 urea acuta, but only 1 Nerza acuta. So very likely that MTR complex originated after MCR, and this Nerza acuta got the MTR gene through horizontal gene transfer. And also that the methyltransferase gene was found that widely distributed in archaea in different phylum, and then they are likely vertically transferred and more ancient than the MTR encoding genes. So these are the different phylogenetic analyses. So the question is how to link the phylogenetic tree with the time tree. So we want to know when those methynogens originated. So here we collect the phylogenetic tree with the time tree to have a better constraints using geological fossils. We use the method conducted by Wolf, the paper 2018, that they use cyanobacteria fossils to make the time constraints. And then we know that in cyanobacteria, there are a few genes transferred from archaea, and then we can use those genes and build the phylogenetic tree, and then use the cyanobacteria time as the time constraint to infer the time of the methynogens. So here we can get the time from the molecular dating. Here shows that, okay, the origin of the MCR is very old. It can be dated back to 3.8 to 4.1 billion years ago. It's really old. And the type 2, class 2 MCR missing metabolism arose later, about 3.6 billion years ago, which are consistent very well with an geochemical evidence, which shows that the methane methynogens could be originated from 3.4 billion years ago.
Fengping, you have about 2 more minutes.
Oh, okay. Yeah. So here shows that, and our work shows that the origin of methynogens could be methyl reducing archaea. It use methyl compound and use hydrogen to reduce it, and it not have MTR and WL pathway, and which are a little bit different from former proportion that the first archaea may be a methanogen from CO2 reduction. So these are a little bit different. And another a new finding from our work is that we found that ethane producing archaea could be the ancestor of multi-carbon alkene metabolism. And more interesting findings from the metabolic pathway, we find that in this kind of archaea, there's no WL pathway and no beta oxidation. And then we somehow propose that those archaea probably could produce C2H6, or it could oxidize ethane to CO2. So the pathway is totally unknown now, and also it's possible that multi-carbon alkene could be produced biotically. So we have a scenario that probably in the old time, very no temperature Earth, and methane and methanogens play a role in warm the atmosphere, and then to drive the evolution. And this makes us thinking that maybe methane may assist the origin of life in other planets. And with this, I would like to thank my funding agencies from National Science Foundation of China and my university, and also the Ministry of Science and Technology of the People's Republic of China. And with this, I thank you very much for listening.